As you can tell, I'm teaching from home today since campus is closed. And not too long ago, the lights flickered in the house. So if I suddenly disappear from this meeting, then you know that class is over, and I'll figure something out after the loss of power that would have caused that. So we'll just see how things go. Okay, some announcements. I have prepared. Actually, I'll go ahead and write these into the notes. Okay. This has to do with the first test that's coming up. So I have prepared a practice test and its solution. So I will put those videos available on the home page in Canvas, and also on my site. They'll be posted on the lectures page. All right, so after class, when I post the things I usually post, like today's notes and the video link, I'll put these out as well. So be sure to take a look at those. The coverage of the tests will be through lesson 12. So that will be covered on Wednesday, so then you'll have seen everything that applies. Okay, also next Monday, 22nd, that class period will be devoted to a review. Basically, I'm going to go over the practice test, and so bring your questions about those problems. And then on Wednesday, 24th, the test will be posted in Canvas. So on that day, there will not be class. And then the test is due that Friday evening. Okay. As you know, I've been relaxed about homework deadlines. I will be much less so about this. I want it by 11:59. If there's if there's extenuating circumstances, then you do need to contact me about this. So this I am going to be enforcing unless there's a legitimate reason otherwise. Okay, so so keep an eye out for this later today or maybe by tonight, and at least see. I think all problems except the last you'll be able to do after today, and then the other one on after Wednesday, and see how those look. Okay. Now, one point I want to make before I get into today's material is I graded homework 2s over the weekend. So one comment I want to make about that is when you're solving a problem by separation of variables, there are some cases where you would write the solution as a linear combination of functions of this form, sine n pi x, which we have seen in certain examples. Whatever is a so whatever linear combination you have in your solution depends on the boundary conditions and, by extension, the domain of a problem. So I want to make sure to emphasize that and give a few examples based on problems that we've seen. If the boundary conditions are, for example, u is equal to 0 at the boundary, both boundary points, and the domain is 0 to 1, then your spatial functions will be sine n pi x. Okay. And only that situation. Otherwise, it's going to be something different. So if I generalize just a little bit, suppose we're on a more general domain, x going from 0 to L, then you're just going to adjust accordingly. So it'll be sine n pi x over L. If it is, let's say we're still in the domain 0 to 1, but du dx is 0 at both boundary points. So that would be cosine. Okay. N pi x in that case. More examples. Let's suppose u is 0 at the left boundary, but it's du dx that is 0 at x equal 1. So in that case, it is going to be a sine. So if you have u equals 0 at the left at x equals 0, it will be a sine function. Oops, okay. But this is going to be a different one. It's going to be n plus a half pi x. To make sure that when you take a derivative of this, that's going to be a multiple of cosine n plus a half pi x. And cosine of that would be 0 at x equals 1. This comes up in one of the homework problems. And one more that we have seen. If u is 0 at the left boundary, but then we have this boundary condition at the right boundary, so it's a mix of u and du dx, then we have a sine because of the left boundary condition. So in fact, if you have u equals 0 at the left boundary, it will be sine lambda nx. It's just a matter of what is lambda n. So in this case, right, so that's what we have in this situation. That was from a few lessons back, because when you substitute this in here, then you get cosine of lambda n plus, lambda n cosine lambda n plus h sine of lambda n. And then you solve that, and you get this. So it should be a lambda subscript of n here. So there was one problem in the homework where these eigenfunctions were called for because these were boundary conditions, but some of you put these instead. So in general, xn of x is going to be some linear combination of a sine and cosine, What is linear combination? You enforce the boundary conditions, and that will tell you what are the values of lambda n that actually give you solutions satisfying the boundary conditions. And is it going to be a sine or a cosine, or it could be a combination of both. So, so be sure to pay attention to this for whatever problem you're given. And for certain boundary conditions that pop up often, it's a good idea to just know these off the top of your head. Some of these do come up fairly often. But if you're not sure, enforce the boundary conditions, and the correct solution will then pop out. So questions about this?
So when we're solving a problem, we don't have to go through the entire solution process that's taught in the separation of variables lesson. We can just immediately go to these.
Yes, you can. So just make sure you have the right ones. But yeah, certainly there's a few that you definitely want to have in your mental cache, like especially these first three come up fairly often. But yes, I mean, like if this is a boundary condition, this is something that we've dealt with in class. You can go ahead and jump straight to this. I mean, when going through that lesson, I needed to show you where those come from, and if I gave you a problem with a boundary condition that you had not seen before, then I would expect you to go through in that case, just because you wouldn't have any way of knowing off the top of your head what the Eigen functions were. But otherwise, yeah, just go with it. Other questions about your spatial solutions? So I'll just write down what I said earlier, general case. We have this, or in some cases, you may have a linear function of x. And to get the specifics, like what are these constants, or what is lambda n, you use a boundary condition to tell you. So a lot of cases, like for example, these boundary conditions right here, you end up finding that you don't have this because the only way to satisfy the boundary conditions is for everything to be 0. You need to have a non-trivial solution. But for example, these boundary conditions right here, du dx is 0. You end up getting a constant function from this. Like bn ends up having to be 0, but an does not have to be. So a constant function of the possibility. Okay. And let's see. So a couple more general points I can make. If this is your boundary condition, it will be some kind of sign. If you have du dx at x equals 0, it definitely will be a cosine. And the specifics of what sine or cosine you get will depend on what is happening at the right boundary. And so here are some things that you can like go to the bank with, at least for any problems that we'll see in this class. Actually, we get to the very end of the semester, we deal with Laplace's equation. We'll see some cases where, because what we've seen before is you would consider the separation constant being positive, negative, or 0. We'd have to rule out positive because it would never satisfy the boundary conditions or give exponential growth. This would come about from a 0 case if it would work, and this would come from a negative case, which always works in these problems. But when we get to Laplace's equation, we'll see some cases where a positive separation constant would work. So we actually start seeing some exponentials, but that's not until like the very end of a semester. All right. So now I had talked about integral transforms before. So now I'm going to focus on the development of that and how it relates to Fourier series, which is what you've seen in various problems involving separation of variables. But here I want to focus on where we have periodic boundary conditions. So let's suppose we have f of x being a periodic function. So for example, maybe it's periodic of period 2 pi. So it repeats like so it's defined like minus pi to pi. So when it has periodicity of whatever kind, we can write it as a Fourier series. So this is the most general form of Fourier series. So for convenience, we're going to work with the interval like from minus L to L, because that has a length of 2L. So we have a linear combination of sines and cosines, where n has to be positive. For cosine, n equals 0 is allowed, because cosine of 0 is 1. So we get this constant term here. And how do we get these coefficients? From inner products involving integrals. So for an, we're doing a inner product of f of x with cosine n pi x over L, and then for bn, we have the inner product with sine. When I say inner product, it means we're multiplying the functions together and then integrating over this interval of length 2L. The reason why we have a0 over 2 is that makes it possible to have a nice uniform definition of all the an coefficients, including a0. If it weren't for 1/2, I'd have to define a0 differently. All right. So actually, let's start this on a new page. So these coefficients that we have, the an and bn, that give us the coefficients of this Fourier series, together they're called the discrete Fourier transform of f of x. And it's discrete because these coefficients are defined on a discrete domain, where n has to be a positive or non-negative integer, as opposed to the continuous Fourier transform, where we're working on the function defined on minus infinity to infinity instead of just a interval of a finite width. Now, the way these formulas come about is a property of sines and cosines that we've seen before, that they're orthogonal on the interval minus L to L. So all of these functions, cosine n pi x over L, sine n pi x over L, they're orthogonal. So that would mean that if I took this equation and multiplied it by, like, say, cosine of m pi x over L and integrated from minus L to L, all the terms would go away except when n equals m. And that's how the coefficient am would pop out. So it's the same process that we've seen before with separation of variables. We're using orthogonality to obtain the formulas, these formulas, for the coefficients. So this is a convenient way to represent a function that has periodicity, that because functions like these, it's very easy to compute their derivatives. So we can represent derivatives of f of x very easily, which is helpful for solving ODEs and PDEs. So I want to talk about how the series behaves, what we can expect from it. So if f is continuous, then and notice this is the interior of the interval. If the function is continuous there, Fourier series will converge to f of x at that point. Now, if we have periodicity, so the values of f at minus L and L agree, then the series converges there also. But what if it doesn't? Suppose these values are not equal. How does the Fourier series behave then? It converges to their average. So what could be interesting is, like, let's suppose you have a function defined on minus L to L. It's nice and continuous throughout the interval, but the values at the endpoints do not agree. What's going to happen is the series will converge in all of the interval anyway, except at the endpoints there's going to be a very sharp jump to the average. And what can happen is, if you're trying to use a series like this to approximate f, but you have to cut it off at some point because you can't compute literally infinitely many terms. Okay, and this is here we also have if we have a jump discontinuity, it's also going to converge to the average. What can happen is you actually get some terrible oscillations in your Fourier series. Okay. So this is just formally stating what happens with a Fourier series. That if you take a limit as x goes to a, and the function has different values on either side of x equals a, then this is what the limit will be. But what will happen is, if you cut off the Fourier series at after a certain number of terms, and let's say you were to graph it, and you also are graphing a function f, and you want to compare, you want to see, like, is this really converging to f? What you will find is that wherever f is continuous and periodic, it does converge eventually. But if f has a jump discontinuity, or if the values at the endpoints do not agree, if there's any discontinuity of that kind, then not only will it converge to the average, but near this point, near x equals a, you're going to see very high frequency oscillations, which is very unfortunate, and this is called Gibbs phenomenon. And actually, I want to see if it's possible, because I believe I have the time to do this. Okay. If I might be able to demonstrate this for you in MATLAB. Okay. All right. I'm going to take a few minutes to attempt to do this, and if I find that it's not going well, then I'll figure something out. So yes, this is totally unplanned. Okay. So I need to unshare and reshare, get into MATLAB. Come on. Hello. It's hanging now when I'm unsharing the screen. Okay, now I'm not sure what's going on. Application not responding.
Is it at all connected to our like US, like your MATLAB when you open it to our USM password? Because I know we just changed that, and I think I had some issues with at least several applications.
Oh, no. Well, this is my own personal MATLAB, but
Um,
so the problem is I don't. Okay, so you can still hear me?
mhm.
Okay, because my problem here is that Teams is not responding right now, and I'm afraid to close it down because I have this recording going. And all right, I'm gonna start shutting some other applications down to see if that helps the situation.
Also, if you leave the team and come back in, the recording should still run.
Oh, really?
Yeah,
Even having initiated it?
I think so. I mean, that's been my experience with teaching.
Okay,
But I don't
that's
know.
good.
I mean, for sure, but that's how it's worked for me.
Yeah, well, yeah, because once I trigger it, if it's happening on their end, doesn't really have anything to do with me. Okay, yeah, because it has stopped sharing my notes, which is what I wanted, but now it won't let me interact with the Teams window to do anything else. Okay, and I'm shutting down other things to see if that helps, but apparently it doesn't. Figures. Love how I could just hang like that and literally hang forever if I let it. Okay, well in that case, I'm going to take a gamble. Okay, and force quit Teams, and then I'll come back and we'll see what happens with the recording.
Like, I don't mean like in the whole meeting, just like you leave and come back in. Like
Right.
you leave. Yeah. Okay.
Okay, let's see what happens. Okay. What's weird is it says like you are in this meeting on another device. It's like, no, I'm not. But yeah, it looks like a recording is still going, so that's great. Okay, so now I will share MATLAB. Okay, so I need to create a function that I know is going to have a discontinuity from failing to be 2 pi periodic. And the simplest function I can use for that is just f of x equal x. So I'm going to define I'm going to use a pretty large number of points, let's say 256. All right, to be 2 pi periodic, and then I'll take a vector of x values, n of them exactly. So then my function is just f of x equal x. So then what I'm going to do is I'm going to use MATLAB's FFT function. So the transform of x will be FFT of x. Okay. Now, so this computes the coefficients like an and bn, but it does it it computes their complex form. So if it took a real part, that would give me an. If it took the imaginary part, that would give me bn. So now what I'm going to do, I need to show you what a truncated Fourier series looks like. If I were to reconstruct the function from these coefficients and plot them, it would disagree with x because I'm just transforming it back. But what I will do instead is I'm going to make several coefficients equal to 0. So basically, I have 256 terms altogether. I'm going to truncate it to half that many. So I'm going to zero out certain coefficients. So let's see, 0 to wait. Trying to get my indices right here. Okay, that should do it. And then I'm going to transform back. So this reconstructs a function from whatever coefficients a and b and I have, but it's a smaller set. So now, if I plot my function, the original function, that's just fx equal x. Oh, something's wrong here. Oh, shoot. Sorry, I messed up here. When I did this, I was supposed to multiply that by dx to get points from between minus pi and pi. Okay, and I want to subtract off pi. Okay. So now I'll do that again. I have to repeat these steps now. Okay. All right, so now I have x defined from minus pi to pi. Actually, I want to make this. Okay. I want to make this a little thicker. Hopefully it'll show up better. Okay. All right, and then on the same graph, I want to plot truncated Fourier series. I'll do that in red. Okay. Oh, that did not go badly at all. That went badly. Ugh, this is what I get for doing something that's unplanned. Okay. Okay. If I look at, oh, I see what I did here. I'm supposed to take my transform and bring it back. All right, because I use FFT to get the coefficients in the first place. I use inverse FFT to reconstruct the function from not x, my original f, but my coefficients an and bn. Okay. So sorry, I just plotted the wrong thing there. So because we have a clutter of commands here, I'm just going to repeat the ones that just so we have it all in one place. Minus my mistakes. Okay, so pick number of points, get the grid spacing, get x values equally spaced between minus pi and pi, then get the coefficients an and bn, zero out the higher index half of them, then reconstruct from the coefficients that remain. Okay. And now the graph, okay. And again, I want to make this thicker.
We don't see the plot.
Oh, okay. One moment, please. Let me fix this. Well, I'm glad I didn't see it before because it was wrong anyway. Okay. Oh, did all of you have your hand up?
I was just going to ask about the plot and where it was.
Oh, okay. Yeah,
I thought I was the only one not seeing it.
Yeah. What happened was I need to unshare and reshare. I need to share my whole desktop because I just picked out the MATLAB window that's shared only the MATLAB command window. Okay, so now I'm sharing my whole screen. Okay, so I don't need this. Okay, now do you all see the plot?
Yeah.
Okay.
Yes.
Okay. All right, so now let's make sure I did this correctly. Plot a reconstructed series in red. Okay, yes, now it looks like how I intend. But I also want to make that a little thicker too. Okay, so, and I'll now make this bigger also. All right, so the red curve in the interior of the interval closely resembles f of x equal x. But because the function is not 2 pi periodic, we have this value at one end, this value way over here at the other end, then even though the series is converging to the correct values as the number of terms goes to infinity, because I've truncated after a certain point, we have these terrible high frequency oscillations. And that's what's called a Gibbs phenomenon. So Fourier series are not so good for functions that are not periodic, or if they have a jump discontinuity in the interior of the interval, because then you cut off a series after a certain point just for practicality of computing it, and it turns out it's not really a good approximation. You might think, oh, if I compute many terms of my Fourier series and stop after a certain point, the coefficients are generally going to 0 as n goes to infinity, so it should be a good approximation, right? Well, no. Not under these conditions. So I just want to show you this is what Gibbs phenomenon looks like. A truncated Fourier series, when it's not continuous and periodic, you get this bad behavior. Okay. So now, returning to Fourier series and Fourier transforms, and what we've seen is if you're solving a PDE on a bounded interval, and you have your boundary conditions, initial conditions, then Fourier series of this kind are very helpful for that. And these basis functions, a cosine n pi x over L or sine n pi x over L, come from this ODE that comes out from separation of variables. This is a Sturm-Liouville problem. And for right boundary conditions, these are the solutions. And also, or if the boundary conditions are periodic. So there are problems, PDEs that have periodic boundary conditions, and that also would lead to solutions like this. And then the coefficients, an and bn, you get those from the initial conditions, like we've seen in separation of variables. Okay. Now, one term I want to define is called the discrete frequency spectrum when you have a periodic function. Okay. So the way that's defined, you have your an and bn coefficients from your cosine and sine terms. So you take a square root of sum of squares for each n, and it gives you Cn. So this is the set of all coefficients Cn make up the discrete frequency spectrum. And for convenience, because A's are defined for n equals 0 and on up, and B's are defined for n equal 1. And 1, 2, 3, and so on. So for convenience, we define B0 to be 0. So what is the meaning of Cn? If you think of a Fourier series as a sum of waves where n pi over L defines a frequency, then the discrete frequency spectrum gives you the amplitude of this wave for each frequency that we have. We recall in the trigonometry class, for instance, plotting sines and cosines and computing our period, amplitude, and phase shift. So that's what we have here for amplitude. So this describes the function's frequency content. So for example, suppose most of these coefficients Cn are 0. Then the ones that are non-zero would be the only frequencies that the function has. So like if f is a sum of just a few waves, then the Cn would be the amplitudes of those few waves. Now, everything I've shown you is for functions defined on an interval minus L to L, so period 2L. So now, let's see what happens when n goes to infinity. Or sorry, not n, L. When L goes to infinity, so this interval minus L to L ends up eventually taking up the whole real number line. So when that happens, instead of having an infinite series, what we have is an integral representation of f of x. And these functions, a of xc and b of xc, this is a Greek letter xc, which some people, including myself, have difficulty pronouncing. So I also refer to this Greek letter as squiggly. So these functions, a of squiggly and b of squiggly, are the Fourier cosine and sine transform of f of x. So what we have here is something very similar to what we saw before, formulas for an and bn, but now we're integrating from minus infinity to infinity instead of from minus L to L. Okay. Now, if f is an even function, like cosine is, then we end up just getting the Fourier cosine transform that we saw last lesson. If f is an odd function, then we get a Fourier sine transform for functions defined on 0 to infinity. Because if we had a initial boundary value problem where you only had a boundary condition at x equals 0 and the domain is 0 to infinity, then these are the transforms that we would use depending on which kind of boundary condition it was. So now we have a continuous frequency spectrum that's defined the same way as the discrete frequency spectrum. It's just that now instead of being a sequence of numbers like C1, C2, C3, etc., we have C as a function of squiggly that comes from these this cosine transform and sine transform. Now, I want to show you here using this expression for e to the I theta in terms of sine and cosine, and vice versa. We have the following. If I write f of x in this manner, then what I want to do is obtain an alternative form of the alternative integral form of f of x. That's a little easier to work with. So what I've done here is I've taken my formulas for A of xc and B of xc and substituted them in here, here and here. Then, in each integral, I rewrite each cosine and each sine in terms of these complex exponential forms. Now, okay. All I'm doing here is I have, I'm pulling out this factor of 1 over 4 pi. And so now I have these factors put together. And I just moved the dy to the outside. So now, what I can do is when I FOIL these, some terms will cancel. And once they do, then I wind up with this. So everything went away except these. And here I took products of exponentials and combined them into one. And so I'm subtracting exponents. Now, I need to put, okay, so then this just simplifies to this, but I want to show you why it does. So I have to put an intermediate step here. Okay, because here I have okay. If I break this up into two separate integrals, make sure I'm on the right line here. Okay. Okay. So I'm going to put each one in its own integral, and these are added together. Okay. Now, what I'm going to do with this one is I'm integrating with respect to xc and also with respect to y. So what I'm going to do is I'm going to make a substitution. Because notice xc is going from 0 to infinity. So I'm going to make a substitution here where xc is replaced by minus xc. So when I do that, and wherever we see xc, it's going to be minus xc. But in the exponent, that's just going to change the y minus x to x minus y. So now these are the same. Now, as far as the limits are concerned, before they were 0 to infinity. But now, with the substitution replacing xc with minus xc, it's going to be from minus infinity to 0. The reason for that is when I do a substitution, that introduces a minus. Then I flip the limits to get rid of a minus. So now the integrands are exactly the same, and we have two disjoint intervals from minus infinity to 0, 0 to infinity. I add them, and now I'm integrating over a whole domain from minus infinity to infinity. So it's doing a substitution to account for negative xc that gives me this. So now, if I break this up, 1 over 2 pi to 1 over square root of 2 pi, 1 over square root of 2 pi, and now I have this part in square brackets. What I have here is the Fourier transform, or continuous Fourier transform of f of x. This was defined last lesson. Okay. Oh, Dale? See yourself hand up?
Sorry about that. I didn't realize I needed to put my hand down.
Oh, okay. All right. Okay. So this equation that reconstructs f of x on the whole real number line from a Fourier transform, that is called the inverse Fourier transform. So when we're solving a PDE on the entire real number line, so there's no boundary conditions to speak of. All we have is just a PDE and an initial condition. Then this Fourier transform is useful for that, because if I need to take derivatives with respect to x, then I end up just multiplying by here we have by IXC. So it's very easy to express a Fourier transform of a derivative in terms of a transform of the original function. So when you have especially PDEs of constant coefficients, you end up reducing the PDE in x and t to an ODE in just t. Okay. So we'll be dealing with Fourier transform more in the next lesson, but I want to show you where this Fourier transform, how it's derived from the discrete Fourier transform that we've been implicitly dealing with already on a bounded interval by letting the size of that interval go to infinity. And how this complex exponential form of a Fourier transform relates to this form that has only real valued functions. Okay, so any questions about what happened here, or we have 20 minutes left. Does anyone have any homework questions? I will say that everyone did quite well in the second homework. I am concerned about the fact that not everybody has been turning the homeworks in. I think most people who are here now have been doing that, but and I see that a few people have already turned in the third homework. So for the rest of you, everything's going swimmingly with it? Or you haven't gotten around to it yet?
I've been working on it, but it's not going well.
Oh, okay.
So it probably will not be done tonight.
Okay. Or any questions you want to put out there?
No, it feels like I'm going back to the very beginning on every single problem, and I'm just getting lost in a sea of technical stuff that I'm not putting together properly. So I'm making it way harder on myself than it needs to be.
Okay. Sorry, just hold on a second.
So like we were talking earlier, I think I need to start analyzing those boundary conditions at the outset of the problem.
Yeah.
And getting straight to the solution that satisfies the PDE and boundary conditions, so that I can then start getting to the solution fast.
Okay. One thing I want to mention about one problem in particular that I have gotten questions about. This is the first problem of a bunch, 7.1, and if I will bring that up here. So I'm trying to. Okay. Lesson 7. Okay. All right, so what I will say for this problem is mainly what I'm interested in is that you have the correct form of a solution, in particular, like having the right eigenfunctions, your xn of x that satisfies the PDE and boundary conditions. And and then, but you show the correct formula for the coefficients that are needed to make sure the solution satisfies the initial condition. I'm not interested in you actually carrying out the integration that would be required for those coefficients. That's really more of a Cal 2 exercise. But if someone either already has done it or wants to do it for extra points, I'm fine with that. But again, it's not the focus of this problem. I want to make sure that you have understand the separation of variables procedure. What are the coefficients that make sure the solution satisfies the initial condition? What are the eigen functions or basis functions that are required for this boundary condition to make sure that your u of xt will also satisfy the boundary conditions. Now, once you have the solution, then you can see like what happens as t goes to infinity. To see what the steady state solution is, because what happens for certain problems is that as t goes to infinity, like especially when you have decaying exponentials, the solution is going to converge to something. What is that something?
It should converge to 0.
I won't talk about giving away answers, but yeah. but this is something.
Sorry, I thought you were waiting. I thought you were waiting for an answer.
Oh no! I'm just talking about how to approach this part of a problem. That it comes from a behavior as t goes to infinity. Okay. And so you're also assigned, okay, this problem, number 2, which emerges in a natural way from what you have to do for number 1. And then there's also lesson 9. Okay, so here we have a non-homogeneous problems. Okay, and I had assigned 2, 3, and 5. So going off of the example I showed from the notes for this lesson, here we have your source term that consists of these 2 terms here, and then in this case the initial condition is 0. The solution procedure I showed you takes this initial boundary value problem and gives you a family of ODEs to solve for n equals 1, 2, 3, etc. Now, the only values of n that you need to deal with are values of n for which you'll get non-zero coefficients either from your source term or from your initial data. Because like in the example in the notes, we had a situation where one of us had like sine pi x and the other was sine 3 pi x. And so for n equals 1 or n equals 3, you would have something. But for all other n, the appropriate coefficient of your source term and your initial data were both 0. When that happens, there's no ODE to solve because your solution to that ODE for that value of n is just going to be 0, so you can ignore it. So when you determine, based on your boundary conditions, what your Eigen functions are, your xn of x, if your source term is a linear combination of those, well, that gives you the coefficients. There's a homework problem, a homework 2 problem like that, where you can just read off the coefficients, and that's a big time saver. Because in the notes, actually, let me pull those up here. See, I think that would have been last Monday. Yeah. Okay. So, okay, here's the whole solution procedure. And you need to compute these coefficients. Now, to get these coefficients of your initial data and your source term, you can always just compute these integrals, but in certain cases that would be a pain, because if your function phi or your function f of xt already is a linear combination of whatever xn of x you already have based on your Eigen functions or your boundary conditions, then you don't need to compute these integrals. You can just, the coefficients come directly from the coefficients of it in that linear combination. Like that's what happened here. We only have Fn for n equal 3. And here we only have An for n equal 1. So here we know it's something of its form, and we can just get the coefficients from here, from what's given. So that's something to keep in mind whenever that comes up as an opportunity to save yourself some time. Same would apply in number 3. Okay. Here what would happen is, all right, this whole lesson is about non-homogeneous PDEs, but this PDE is homogeneous with a non-homogeneous boundary condition. So you have to apply the procedure from some lessons back to transform a boundary condition into one that is homogeneous, but that's going to add a source term onto here, and it'll affect the initial data also. Then this initial boundary value problem is in the correct form to use the procedure from this lesson. So you're combining techniques in that case. Because if we're going to have, because one of the points of this lesson is, if you have to put up with non-homogeneity somewhere in your IBVP, you'd rather have it in your PDE than in your boundary conditions. All right. Yeah, but certainly, the tips I gave earlier today for for certain boundary conditions, what are the appropriate Eigen functions, by all means, take advantage of that. So, any last questions in the 6 minutes we have? But definitely, if it feels like you're spinning your wheels on these, let me know about it, because then I can I can help deal with that. Because certainly there's a lot of all of these problems, but there are also ways to take shortcuts based on what we see from one problem to the next. The goal is not to have you go through reinventing the entire separation of variables wheel every time you take on one of these problems. Oh, sorry, Walker. I just saw your comment now. I wasn't sure what it was related to. Oh, okay. All right. All right. Last chance for any questions. Okay. I will stop recording here, and let me know what's going on with the homework if needed.